Come on. All right. So my little dilemma, if you really want to call it that, is that so I looked at the schedule for a class. I was like, okay, what am I supposed to cover this week? And I see the sections on my site. Okay, well, I'll go to my notes and see how much that is. And it starts here, this little paragraph, and I'll do this so Caitlin can see. Yeah, so this little paragraph right here, I have to cover this week. And then this little portion of this page too, so that's less than a page for the week. Not sure what I was thinking there when I made the schedule. And I probably could BS about that to an extent. I can BS about all this stuff, but let's see. And then in the coming weeks, well, okay, next week is a short week because we have fall break, so we only have class on Tuesday. And actually, I have more set up for that day. Well, this doesn't make any sense. Okay, and then the week after that is when I do like multi-grid and conjugate gradient type stuff. So, okay, I'm going to rebalance things because this is kind of ridiculous. Okay, page 31. Okay, all right, so I will extend a little bit further just so I have something to cover and less to deal with next Tuesday. After I cover whatever it is I'm going to cover, then we'll see where everybody's at on the homework. And hopefully some of the messages I sent that based on questions that I've got lately, I've updated the homework hints file that's paired with all the assignments on Canvas. Because I totally forgot that I'd written in the hints file to do one fourth order stencil and then advise you in class to do another. So I needed to resolve that discrepancy. Okay, so let's see, and all of you here took 610 last spring, right? Okay, yes, and Caitlin also. Okay, well that's good. At least everybody's on the same page here.
For some reason, I do not feel like it's the fall semester. I'm so lost in time.
Oh, yeah. Yeah, I tend to forget that too. It's like where we're at in the year. It's all runs together. And it doesn't help matters that no matter what semester we're in, we're always thinking about all the other ones, like thinking ahead to the next year, that sort of thing. Like, stop. Okay, so so you know this is a numerical methods for PDEs class. Today it's all about AX equals B for PDEs. Because certainly, as you've seen in the homework, you are dealing with that. Like if you're solving Poisson's equation, when you spatially discretize it, you wind up with a AX equals B problem to solve. So a focus for today is direct methods as opposed to iterative methods, which I'll talk about more next week and the week after. Okay. Now, and the thing is, we learned all about this in 610, but that was a while ago. There's been plenty of time to forget. But also going to keep in mind the kind of problems that we're dealing with here, where thankfully typically involve sparse matrices. Okay, so So first, the general case. So, and to be precise about that, where matrix A is n by n invertible. But at this point, we're not making any other assumptions about A. So then, for direct methods, you would use the method of choice is Gaussian elimination. With partial pivoting. With partial pivoting is particularly important to reduce propagation of round-off error. And your output of all this is this factorization. P times A is equal to L times U. And as you recall from 610, matrix L is, and you know what? Since you guys took 610 virtually, so I wasn't writing things on the board, so I would have a shorthand for certain classes of matrices. But since I was typing everything in my LaTeX document, I would not need it. So L is a lower triangular matrix. I never liked writing out lower triangular. So I would just use this symbol to indicate lower triangular. But there's another property that L has. It's not just lower triangular. You don't remember what else is true of it. Unit lower triangular, meaning the diagonal entries are all 1. So to indicate unit lower triangular, I'd stick a little 1 here. So that's my shorthand for unit lower triangular. And then matrix U is upper triangular, but not unit. Since triangular systems are far easier to solve, order n squared operations versus order n cubed in the general case. And then the matrix P is a permutation matrix. Not a good idea to generate explicitly. You can represent a permutation matrix as a vector of scrambled row indices. So this is just a row interchanges that were applied during Gaussian elimination or partial pivoting, so that the LU decomposition would exist. Okay. All right. And then I said, and then you use forward substitution and back substitution to solve a system from there. Now, in certain cases, if A is sparse, you can make a statement about how sparse the L and U factors are. For example, if A is a banded matrix, like for instance, what you're seeing in problem 2, whether it's a second order or fourth order method, you have a banded matrix, either a tridiagonal or can have 5 or 6 non-zero diagonals. Then that imposes a limit on the bandwidth of the L and U factors. So those systems can be solved much more efficiently. But once you get to like 2D problems, yes, the matrix is still sparse, but it's not banded anymore. You have non-zero entries scattered around more. Even though there's a pattern to them, it can be difficult to ensure sparsity of the L and U factors. But I'll talk more about that in a moment. Okay. So that's the general case. And then, if a matrix A is symmetric, positive, definite, okay, so, and just to refresh your memory on that, A is symmetric, but you also have X transpose AX is strictly positive whenever X is a non-zero vector. Then you can use Gaussian elimination. You can actually, it's proven that you don't need to pivot, but it's not the best way to go. What is the best way to go if we're talking about direct methods? There's a, yeah, that's one of two options. So there's Cholesky. So still a factorization into a lower triangular times an upper triangular matrix. So G is lower triangular. It's just at this time, because of the symmetry, the LU, the L and U are transposes of each other. Also, the diagonal entries are strictly positive. That's to, their requirement is to ensure uniqueness. Okay. There's one other closely related factorization. It's the LDLT, or so LDL transpose, where L is unit lower triangular. In fact, it literally is the L from the LU decomposition. And then D is a, this is my shorthand for a diagonal matrix. Some prefer the LDLT factorization because it doesn't require computing any square roots. Cholesky factorization, you do have to take a square root to get each diagonal entry of G. So in fact, LDLT is referred to as the square root free Cholesky. Now, in this class, as opposed to 610, we're not really concerned about the nuts and bolts of these methods. And there are functions in MATLAB to do all these things. You can use the LU function to do the LU decomposition. Of course, backslash uses Gaussian elimination of partial pivoting. There is a function chol, C-H-O-L, for Cholesky. There's even a, actually, I want to make sure I get the name right. There is a function for LDLT. Okay, it's called LDL. So I'll write the MATLAB functions to the left. So LU, chol, and LDL. We'll implement these factorizations. Okay. All right. And the backslash operator is actually quite sophisticated. That by default it would do Gaussian elimination of partial pivoting, but if it detects that the matrix is symmetric, actually I believe it will use this because, what was that? Okay. So when I hear that noise, it tells you like something went wrong. But
You got Samsung's phone.
oh, okay. All right. Okay. Well, at least nothing's going wrong.
Only reason why I called him out because I didn't want you to think something was wrong with your computer now. That was his phone.
Okay. Well, thank you.
You're welcome.
Okay. No, I can't really recall the last time like I actually had trouble during class with phone use. Maybe to the point where I just don't care anymore, or it's mostly graduate classes, so again, I don't care anymore. But at UC Irvine, it happened a lot, and I would make some remark about people silencing their phones, whatever, and they get pissy with me. It's like, hello, you messed up. Don't do that. Don't get mad at me over it. But yeah, so.
What do you mean I'm not allowed to have my phone on me during the test?
Yeah.
It's the same with middle and high school kids.
Oh.
They get the same way when you mention they have a phone out.
Yeah, well. Yeah. It just goes to show people just, you know, they want to do what they want to do, and And how dare anyone suggest otherwise, so.
If I got called out for that, like, back in junior high or high school, I would get embarrassed, you know, not that it's.
Well, yeah, that's, you're old fashioned.
Okay, my phone went off one time when I was in high school, and I got in trouble, and I'm just sitting there like, crap.
Okay, so, so backtrack to something that's tries as much as possible to take into account what kind of matrix you're giving it, like checking for symmetry, or of course it would check for triangularity too, so there's no need to do Gaussian elimination or any other factorization. Okay. Oh, the other thing I wanted to make sure I point out that the cost of these factorizations in terms of how many floating point operations. LU is roughly 2/3 n cubed, whereas Cholesky or LDL is about half that. So that's another reason why you want to use those methods in the symmetric case. Okay. Okay. Can Dr. Schroeder please send out fewer emails? Okay. All right. Okay. So, after all the time yammering about this one little bitty paragraph, my BSing game is on fire today. Okay. Questions about? Well, I've already said much of anything, but. Okay. All right, but it's important to keep this in mind as to which factorization to use in certain situations. I remember when I was teaching about symmetric positive definite matrices in classes like 610 or 561, pointing out that when you have that kind of matrix, then you really want to think Cholesky, because it's helpful for so many things, whether you're trying to prove something about it or for solving a system involving such a matrix. And I knew it finally had some success when one year when I was reading my student evaluations, and there was so one student had as the entirety of their comment was, and I quote, "When I think symmetric positive definite, I think Cholesky." And actually, because of the small size of the class, I knew who the student was. It was my co-author, Amber Sumner. So that was a proud advisor moment. No, because it's something I felt to drill the students' heads, but as a reflex, like, oh yeah, this kind of matrix? Okay, then this is what comes to mind, or this. Okay. Now, I mentioned earlier the issue of sparsity. And the ideal situation is when the matrix is not only sparse but banded. But as I mentioned, like with 2D problems, for example, you can't really count on bandedness. So, and the problem is when you have sparse matrices, any of these factorizations may destroy sparsity. So A could be sparse, but if not banded, you have no guarantee that the L or U factors will be sparse, or similar factors that you have here. And that's one reason why the other category of methods are often used, iterative methods, because you don't have to deal with the situation of having a factorization wreck sparsity. But iterative methods have their own issues. So I want to talk about sparsity for a bit. This eraser definitely sees better days. I saw another one here on the floor. totally safe to touch, for sure.
Well, I know the only reason why the board was erased was because Dr. Lee was not presenting today.
That would do it, yes.
It was Sarah giving a presentation today.
Ah, well, I should ask her about that. I know that could be a stressful occurrence.
It's only stressful when Dr. Lee interrupts the middle of your thought and goes, "No, that's not right." And I'm like, you couldn't have waited for my thought to finish.
Yeah, he does that.
It's okay. Robert got fully inducted to that too.
Well, it's extra good when it happens in the middle of a defense.
Yeah, yes it is.
Yeah.
He literally told me, "Oh, I was extra hard on you so your committee members would feel sorry for you."
It worked.
I figured it's safe now that the degree has been processed and I have it. It's safe to
Yeah.
share that story.
Yeah, although I did unwittingly do literally that to Chandler this morning, so. I had to apologize for asking the hardest question. Okay.
Walker started getting offended on my behalf because she's like, "He was so mean." And then Robert and I were both like, "He's not normally like that."
Like, when it started, I was like, I'm not used to seeing this, Dr. Lee.
Okay, well, I'm just glad that lately anyway, Dr. Schroeder has not accepted my standing invitation to attend prospectuses and defenses. Okay.
Yeah, I'll cry because probably by the time I go to do my defense for the PhD, it'll be normal. So he'll be there in person.
Same.
Well, the nice thing is he's over in another building now, so.
Oh, never mind. We might not have that happen.
Yeah. So
Unless he happens to be here for some reason.
well, he still has his office here, but
Oh.
yeah, he's mainly over there. Okay. All right, so what can be done, if anything, not a whole lot really, to preserve sparsity? So the problem that we have is that pivoting, when you're doing gas elimination or partial pivoting, has a tendency to destroy sparsity. And this is the troublesome phenomenon called fill-in, where new non-zero entries are introduced to the matrix as you perform row operations on it. So even if you have a matrix that is banded, if you start pivoting, then that wrecks the band. And then the sparsity goes with it. Now, a good idea to check sparsity in MATLAB is a nice command you can use. Spy of a matrix. So what it does is that puts up a graph where the non-zero entries are shown in blue and everything else white. So you can see the structure of a matrix. So for instance, if you do spy of A and see that it's sparse, that there's only a few blue dots there, and when you go ahead and do the LED composition and you do spy of L and spy of U, and you see that maybe you're all filled in, then things went badly for you. You might need to try a different method. Okay. Now, one thing that can be done to help preserve sparsity is there's no, I don't recall the official term for this, but basically relaxed partial pivoting. And what I mean by that is, well, first of all, is there anyone who remembers how does partial pivoting work? How is it decided which rows to swap? Like, what's the criteria?
scientist.
Yes, you want the largest entry to sit on the diagonal, to have the largest denominator in your multipliers, make your multipliers smaller. So what you can do is, so instead of requiring that the multipliers or the entries of your lower triangular factor L be less or equal to 1, which is what partial pivoting does, maybe you choose some other factor, like so m greater than 1. So you're still imposing a bound. You're not allowing the entries to get arbitrarily large. So that can still help with the main aim of pivoting, that is to contain propagation of rounding error. So this gives you a choice of rows to swap. And maybe you can make a choice that will help preserve sparsity more than the choice that partial pivoting would make. Okay. Now, there are some, okay, so this is one thing you do. For certain problems, this is limited, there's a red-black ordering. And what I mean by red-black ordering is, if you just mark alternating rows or columns, be red, black, red, black, red, black, and then you rearrange them to have all the red rows together and all the black rows together, then in certain cases, that can lead to an advantageous structure as far as solving a system of equations. Again, the usefulness is pretty limited, but this does come with certain problems involving PDEs. Okay. In particular, one I've shown you, the 2D Laplacian. Because what that can do is if you do red-black ordering on the matrix you get from finite difference, 2D Laplacian, then you have the diagonal blocks are diagonal matrices. So that's some nice gain in sparsity there. Okay, now, but here's some other things you can do that are more generally applicable than this. So if you have so this MATLAB function, call AMD. So you give it a matrix, and it will return a permutation matrix. And what you do is you use this permutation matrix to do your row swaps in Gaussian elimination instead of partial pivoting. Then when you take the LU factorization of P times A, then the LU factors will be as sparse as possible. So it tries to figure out like optimal row interchanges to preserve sparsity. Okay.
What is that command P equals?
COLAMD.
Okay, I just wanted to make sure that I was reading that correctly.
Okay. And then there's a similar command for symmetric matrices, SIM AMD. So if your matrix A is symmetric, then this will give a permutation that you have to apply to the rows and columns, because you shouldn't really do pivoting. You should not do just row interchanges on a symmetric matrix, because it'll wreck the symmetry. But if you swap rows and then you also swap the columns in the same way, then you're doing like P transpose, which is still symmetric. So this will give you a permutation matrix so that if you swap the rows and columns according to P, and if you do a factorization like LDL or Cholesky, then again, the factors will be as sparse as possible. So this is something that can help for more general matrices. So the goal for these two is to reduce fill-in. Any questions about any of that? Okay. Oh, I'm actually halfway through the class period, so I can treat myself to a 5-minute break. So I haven't done that lately.
When we get P.
What?
When we get P.
Yeah.
When P equals school,
Yeah.
A and B. What do we do with the P? We multiply by 8 so that.
Yeah, so you compute P times A, and then that does a row interchanges. And then you take the LU factorization of P times A. In that case, no pivoting because the pivoting's already been done. And then similar with sim entity, you compute PA, P transpose, and then you can do like Cholesky or LDL factorization of that. So basically doing all the pivoting up front, and then do a pivoting free factorization after that, where the resulting factor should be less sparse than if you were to do partial pivoting.
Sanchez, have we convinced you to get a pet fish yet? This is when Robert just shows up at your house with a fish for you.
I'm pretty sure Stanton would just tell me to leave him alone.
I'm ready for a nap. You know what else I forgot to factor into the money I spent this week?
What?
My gas, the gas money I've been using in my car. I drive out the pedal constantly.
It's true.
I love it though.
That's what peak performance looks like.
Oh, Chandler, has anyone told you about, karaoke? This Ricardo wants to make sure someone tells.
Okay.
It's tonight at 7.
It's in the
In the
math
math
zone, and she's buying pizza for anyone who comes.
That sounds fun.
She invited all the
Oh,
tutors.
Yeah, she invited the
The
tutors.
ETAs and the tutors.
Because I knew one of them, I can't remember who. My
It's
mind
the
is.
new one.
You know?
I think so.
Yeah, she had asked me and Rachel if Ms. Ricardo had told us about it earlier today.
I will be going to tend to an injured horse. I will not make it.
What's wrong with it?
It's 2 separate issues now. It started as 1, now it's 2.
What is it?
Sunday night, I get this phone call. Something's wrong with your horse. She's lame. She's not putting weight on her leg. And I'm not paying for that emergency vet fee, because that can be like $200 just to have the vet come to my house.
Yeah.
So I was like, let's just keep it on for a little morning. Tomorrow, the vet finally squeezes me into her schedule. She gets out there in the afternoon to check my horse. She pulled a ligament over her stifle, which is basically like our kneecap. So we injected a steroid, hoping for the best. That was just yesterday. Today, at noon, I get a message that, oh, your horse blew an abscess on the foot that's attached to the leg we treated yesterday. Yeah, so she had a foot abscess too.
What is that?
Like an abscess that you would get in your body.
Yeah,
It's just in her foot.
how does that even happen? Like an infection or?
It's an infection, but it's just because it's been raining so much. So now I have to go out once a day, or at least 5 days, to soak her foot
Oh
with
no.
Epsom salt and water.
Aw. I'm sorry.
So,
So I've already spent $700 for the first issue. We're now looking at more money to fix the second one. I'm like, horse, you live with a broke owner? You're owned by a broke college student?
Y'all pull it together.
like Rachel was telling me about her horse over the weekend. I was in my office earlier, I had earbuds in, and I was doing research. All of a sudden, I just hear someone call my name from behind me, and I'm like, wait, what?
I was like, Robert, can we switch presentation days because I want to go check on my horse. Because I have not been out there yet since the abscess was discovered. Because I was like, okay, let me just email my professors. I can get my classes. I can get out of classes. It's fine with issues. Rachel, calm down. It's okay. It's not an emergency. You can wait until after your classes. So I still messaged Dr. McDuffie, please let me spot this because I really want to go check on her. I can present if I have to, but I would really much rather go check on her horse because Jesus Christ, I'm going insane.
I'm just glad he said we're not meeting today, because that means I actually have time to prepare for our meeting.
Because Robert knows about this last week. She also came up late for the same issue that we treated on Monday. So this is an ongoing thing,
Yeah.
which is why I have spent in total $700 on the ligament issue. Just the ligament issue.
So,
We have not even factored in anything for the new
That's
foot.
okay?
We got the cat healthy finally
Woo.
after $500.
so Rachel, I have a question.
Do you want an animal?
So,
Say, do you want a mammal?
An animal.
Oh,
So-
mammal.
you know how
Technically, they're all mammals.
Yeah, I know.
you know how they say
When it rains, it pours.
when people turn 30, their bodies start falling apart.
Okay,
Is
but
it the same thing with horses and twinnies?
Probably.
okay, she is much, okay, to put her age in human years, she's like 70 in human years.
Get it, girl. Well, I've been trying to train my cat to use his inhaler and he hates it, so.
Oh no.
Not as bad as yours, but it's very annoying because I give him a treat and I put it on his face and then I give him a treat afterwards. But he will not let me hold it on his face for longer than
So-
like not enough for him to get even one breath in.
Oh no.
Yeah.
So, my baby cat, she,
Maybe start putting it on his face when he doesn't need the medication.
so the last
That's what
time,
I've been doing.
Oh,
Yeah,
okay.
he only uses it once a week.
the last time I had her feed her medicine, most of the time she was fine. She would let me pick her up, she'd lay in my arms like a baby, like normal, let me feed her the medicine, no problem. Unless my brother was in the same room as me.
Oh no.
He was in the same room, she would freak out and would not let me give her the medicine.
His
Weird.
Kit Kat is a very strange individual.
She discovered I had my keys on a lanyard. So if I have the lanyard hanging down my hand when I go to grab my keys, she will climb up my pant leg trying to get to the lanyard.
You also forgot to describe your encounter of her and your lawn guy.
So, yeah, I look at my yard. She has not tried to go out since this. But several months ago, she went to run outside. I don't know if it's because it was a person or
I've noticed that before.
she got outside, saw him standing right there at the door, looked up, ran back inside.
Okay, I know it's gone longer than 5 minutes, but I don't care.
You're just trying to make the schedule match.
Something like that, yeah. Okay, now, the last thing to deal with is preconditioning. And even though it's mainly for iterative methods, it's a concept that can be applied in general. All right. Okay. Now, so the problem with AX equals B problems that come from a PDE, it is pretty much a given that the matrix A is going to be ill-conditioned. And in fact, as you move more grid points, as your spacing H goes to 0, the condition number of A, which, as you learned in 610, is the norm of A times the norm of A inverse, goes to infinity. So, poor resolution, even worse conditioning, which causes numerical methods, all kinds, a lot of problems. Okay. Now, so to help the situation, you can use following. One is called left preconditioning. So you just multiply AX equals B on both sides by some matrix P. Actually, the way it's written in my notes is P inverse. So the idea is, okay, well, I'll talk about criteria in a moment. There's also right preconditioning. So this is where you multiply the matrix A on the right by some matrix. So we have A P inverse Px is equal to B. So the idea is you let Px be equal to Y. So really you're solving a system A P inverse Y is equal to B. And then, so A P inverse Y is equal to B, and then you solve Px is equal to Y to get the solution X of your original problem. And certainly you can apply both left and right preconditioning in tandem. So the question now is, if we're going to do something, either one of these things or both, how do we choose the matrix P? So P is referred to as a preconditioner. Okay. Now, okay. So here are the criteria. So first, want to choose P so that when you multiply with A over on the left or right, the resulting matrix is approximately identity. So you want P to be a decent approximation of A. So that either one of these would give you a matrix that's closer to identity. So that system would be easier to solve. The second criterion is that P must be easy to invert. So PZ equals W, and just making up generic vector Z and W here, needs to be easy to solve. So for example, right preconditioning, you have this system to solve. So you want that to be quick. During the actual algorithm that you use, and you're multiplying by P inverse, so that has to be easy. It has to be cheaper than if you were just solving the original unpreconditioned system. And the problem is these two criteria compete with each other. And to see that, you can consider the extremes. So the extremes would be P is equal to A itself, or P is equal to the identity. So if P was equal to A, it satisfies the first condition beautifully, but not the second. You've made no progress. If you set P equal to identity, this system is trivial to solve, but then you have no help with this criterion. So you're choosing something in between to try to find the right balance between making a preconditioned system easy to solve and also making the transformed AX equals B problem having a matrix closer to identity. All right. Now, okay. Questions about any of this? Actually, don't have much left, so I'm going to switch to the other half. Now, as an example, some simple preconditioners. If I let A equal L plus D plus U. So L is the strictly lower triangular part, so excluding the diagonal. U is a strictly upper triangular part, also excluding the diagonal. And then D is diagonal. So it's taking, if I is greater than J, you put Aij in here. If I is less than J, you put Aij in here. If I equals J, put it in here. And this decomposition is used for certain iterative methods, like stationary iterative methods, which I'll talk about later. Also, that gets covered in Math 561. Okay, now, so simple preconditioners, like P equal to D, or P equal to D plus L. Now, both of these are good for the second criteria of having a preconditioned system easy to solve, because this is a diagonal matrix, so that's easy to solve. Here, this is a lower triangular matrix, so that system is cheaper to solve than the original system A with A. Now, what about a decent approximation of A? So this can be particularly effective if A is diagonally dominant. So what that means is the diagonal entry, each diagonal entry, is strictly greater than an absolute value, the sum of the absolute values of all the off-diagonal entries in its row. So this is true for all rows. Then we say that A is diagonally dominant, or the proper term is strictly row diagonally dominant. Well, that seems to be the only kind of diagonal dominance that anyone ever talks about. So if you just say diagonally dominant, people will assume you mean this. Okay, because in that case, since the diagonal is by far the most significant part of A, then if you multiply A by D inverse, then you're making all the diagonal entries equal to 1. All the off-diagonal entries will be less than 1 in magnitude. So you've made a matrix that is going to be at least closer to identity. So that could be can help in this case. All right. Other things you can do for preconditioning are called incomplete factorizations. So there's incomplete LU or Cholesky, and these are implemented in MATLAB. So the idea is you find LU factors or Cholesky factor that are approximations of a true LU or Cholesky factorization, with the criteria of trying to ensure sparsity of these factors, so that systems involving these factors are particularly easier to solve. So, for example, you could do an incomplete LU factorization and use the L as a left preconditioner and the U as a right preconditioner. So then the approximate L inverse times A, which is LU, times the approximate U inverse is hopefully closer to identity. Well, I know that Sampson has been using these preconditioning methods in his research, and it's been pretty disappointing, honestly, hasn't it? Yeah, so, and that's what I found before you started working on this. So I feel the need to cover them because they're out there and people work with them, but yeah, they're not great. So at least for the kind of problems that you've been dealing with, maybe for some other problems, they might be more effective. Well, it's kind of a recurring theme that I've noticed in all my years of research, that when I learn about methods like these, or more advanced ones that may not be taught in classes, but maybe find out about them from papers or conferences, whatever, and think, oh, this is something that could be helpful to me. And then I look up the details, and it's like, wow, that was a real letdown. Like, this did not deliver what I needed at all. And that seems to be the case most of the time. And while that's unfortunate, I think, well, at least the disappointing state of research in computational mathematics at this point in time, okay, in my own personal opinion, leaves the door open for people like me or you all to make contributions to it. So there's more room to move the ball forward. So that's my attempt to be encouraging about all this. But I have to say that, like, a lot of researchers, particularly more experienced ones, when they present their research, they give you off the impression that whatever problem they're working on, oh, that problem is solved. Their work is the end-all, be-all of it, as if they don't want anyone else to try to compete with them. And I think it's really fortunate because it creates a chilling effect on further innovation. Because when you look at someone's work, there's always going to be limitations. Sometimes they can be harder to find, but they're always there. There's always a chance to do better, and I think that the way people present their work, because they're trying to get ahead in their careers and so forth, and create the impression that their work is so wonderful. And I think it's created in me, especially early in my career, a sense of excessively high expectations for work that's out there. And then once I get to scrutinize it, then it's like, oh, well, yes, this is something, this is a meaningful contribution, but it's not as amazing as they made it out to be. So, and I think that's why I've gotten very hard to impress. So, anyway, off soapbox for now. But preconditioning is a very active field. There's a lot of work going on, especially for certain problems. For example, problems that come from certain PDEs, people will try to design preconditioners that are very narrow in focus, because it can be quite difficult. Excuse me. So, and then designing preconditioned versions of the direct or iterative methods is, can also be a challenge. As I said, there's only a little bit I'm going to say about preconditioning here, just to communicate the main idea, but that's just like the tip of the iceberg. Okay, now, how are we doing on time? Okay. Okay, actually, yeah, I did reach the end of what I needed to cover for a week, and actually some of next week. So yeah, we certainly have time for any homework questions.
Question 2C.
2C.
Yeah.
Okay.
When we say modify the right hand side, I'm struggling to do that.
Okay, yeah, so, yeah, there's a bit of a wrinkle here. So, okay. All right, so as a problem states, what we're trying to do is change your right-hand side to equal to the original right-hand side plus h squared over 12 d2f, or d squared, second derivative. Okay. Now, so I need to elaborate on what this means, because certainly you're going to take your f and multiply it by your matrix for the second derivative. So minus 2, minus 2, minus 2, ones. But that does not account for everything, because when you take a vector representing a function like f and multiply this matrix by it to approximate its second derivative, this matrix will assume that the boundary values are 0. But while that is true of your solution, it's not true of f. So if you look at your function f, so sine phi x squared, minus cosine phi, et cetera, it's non-zero in the boundary. So really, to get the full second derivative, you need boundary terms. Now, what would that mean in this case? Okay. If you think about the finite standard difference scheme, uxx xi is approximated by ui minus 1 minus 2ui plus ui plus 1 over h squared. So if you consider a case where I is equal to 1, so the leftmost interior point, you're going to have this term for u0, the value at the boundary, x equals 0 in this case. So you're going to have 1 over h squared f of 0 needs to be included. Now, in between, you don't need to add anything because the matrix covers all the differentiation. But then you can have the same thing down here for when I is equal to n, you can have ui plus 1. So that's the value at the right boundary point, x equals 1. So with the inclusion of those boundary terms, then you'll have a full second derivative at every single point. So really, I'm just contributing the missing terms. This one for I equals 1, and this one for I equals n.
That's where I got confused.
Okay.
What we're adding, because we're adding just row 1 and the last row, right?
Yeah.
Are we adding into the D squared matrix, or what are we adding into?
Oh, well, the thing is, it's not part. It can't be part of this because the vector f consists of the values of f of function f of x at only the interior grid points. So this part has only the contributions to the approximate second derivative of the interior f values. And for all I between 1 and n, that's enough. So this accounts for anything that cannot be found in the vector f. So vector f consists of f of h, f of 2h. So points strictly between 0 and 1.
So, because when we implement this on MATLAB, when we multiply this squared times f,
Yeah.
then we just add 1 over h squared of f0 to that matrix.
Oh yeah, yeah. So you compute this vector, and then you add this vector to it, or you can just modify the first and last elements of that vector to include those two terms.
So that was what I did.
Oh.
The solutions were all.
Oh, okay. All right, so maybe I may have to look at that. Okay, so this is what you were carrying out.
I think so.
Okay. Okay, let me ask this. When you were doing this, were you using your matrix from the system?
So the matrix from the system is negative, right? So just
Yeah, so you do need to negate it for this.
Yeah, I did that.
Okay, that's one thing ruled out. Okay. So you're getting a solution that's thrown way off, or?
Like, it's not close at all.
Oh. Okay. And let's see. Peek. Oh, code. Okay, so that's interior parts. We have. Okay, so F1 is. Oh, okay, so we do. Okay. And A is the matrix for minus UXX.
Yeah.
Okay, so then you do. Okay, so 18 pi is the value at x equals 0, I'm assuming.
Yeah.
Okay. So then okay, so F is equal to F1, okay, so it's just, I don't see where you multiply by h squared over 12.
That's it.
Okay. Yes, for the interior part. But I don't think you multiplied this part by h squared over 12.
What are you?
Yes, this is, whatever you're assigning to, okay, so, yeah, okay, yeah, you want to the whole thing by, yeah, okay. Okay, and when you're plotting the error, which is which?
So I just did some of the,
Okay.
I used 50, 100, 200.
Right.
And then I built it again, used 240.
Okay, so, and then, okay, so it's not, so, yeah, so just look at it, it's getting 4 accuracy, it's weird. Even though it appears to be converging. Okay. Yeah, because usually when there's just one little mistake, as you've seen, like it just throws everything off completely. Okay. Now, so the error in this is going to be order h squared, but then that is multiplied by h squared over 12. So the error in F is order h to the 4th, as it should be. And as for the boundary value, yeah, it's going to be okay. Okay. Well, we're out of time. But we'll keep looking at it. Okay, so all right. I can do the same thing on Thursday that I did last Thursday, where it's just like it's just about homework and.
I vote the Tuesday lecture we have on Thursday, so we don't have to come in on Tuesday.
I'll keep it in mind for future weeks. Okay.
But next Tuesday is fall break.
Oh, that's crafty of you, but no.